Einstein's theory of general relativity that explains both the force of gravity and the shape of our universe has a mountain of evidence in its favor, and yet the way it was first developed had a huge impact on our philosophy of time. This philosophy was one that Einstein believed in, that time was another dimension like the three-spatial dimension, and that the universe was simply a four-dimensional structure that we are viewing as passive observers. Nevertheless, Einstein's ideas about time as a dimension remain with us. Science fiction books, movies, and TV shows like Back to the Future, Star Trek, and Doctor Who invoke his theory when they present time travel as a journey from one place in time to another, as if we are traveling from one real place that exists to another real place that exists. But do two whens actually exist simultaneously, or is now the only time that exists? Suppose you are a time traveler and want to travel back to the Cretaceous period and see some dinosaurs. Are those dinosaurs somewhere back there in the past, like a point on a river? Or do you need to rewind the world somehow, de-evolve it to get back to the past? It seems like Einstein's theory supports the former idea. All times exist simultaneously somewhere in our space-time. Just because quantum mechanics throws a monkey wrench into determinism, we all know that we will experience a future once God rolls the dice, and that now will become the past. His theory also has 100 years of evidence to support it, so it seems to be a done deal. But wait, look at his theory more closely and we see how his philosophy of space and time was baked into it, causing it for 100 years to be taught and formulated in the way he wanted it to appear. First, a little history. Working in a Swiss patent office in 1905, Einstein developed what is now called his theory of special relativity. In this theory, he showed how our perception of time and space changed depending on our state of motion. Many of us are familiar with the idea that if a person or thing approaches near to the speed of light, we will see that person or thing slow down. Lengths also change. The length of a ruler accelerated to near the speed of light will have a measurable shortening of its length in the direction of motion. At the time, Einstein did not propose special relativity had anything to do with space-time geometries. Also, of all the papers Einstein published that year, 5 groundbreaking results, it took the longest to confirm directly. Now we regularly observe its effects in particle accelerators, which accelerate matter to near the speed of light. Fast forward a few years and the mathematician Minkowski takes Einstein's ideas and fits them into a theory of space and time. He can show that these strange dilations of time and contractions in length are all the result of how we move around in a four-dimensional space-time relative to one another. Einstein is excited now to take this idea and fit gravity into it. In his theory, the space-time is curved and the curvature looks to us like gravity. He presents his theory to the world in 1915, and in 1919, it is confirmed in observations of starlight passing near the sun during a solar eclipse. Einstein's theory presented the universe as a four-dimensional manifold, which is a word for a shape with certain properties. People and things in that manifold had to move around according to a strict rule: no traveling faster than the speed of light. Traveling faster than light is unfortunately the only apparent way to go back in time in Minkowski's universe. But in Einstein's there was a loophole. Space-time itself could be shaped in such a way that some paths between points were shorter than others. And so, even if you couldn't go faster than light, you could shorten the journey between 2 points. You can't turn around on the highway and go back, but like a cloverleaf, you can take an exit and backtrack by another route. The other property of Einstein's manifold is that there is no such thing as universal time. Everything has its own proper time that it experiences as it slices its way through the manifold. Objects that are near one other and in a similar state of motion tend to experience similar flows of time as well, which is why we all on Earth experience nearly the same flow of time. The variations for ordinary speeds on Earth and small differences in gravitational fields. It seems like all this discussion of bridges between times and places and no universal time means that time works like a highway. There are exit ramps and on-ramps. You can go back in time if you can find an exit to take you by another route. All of this supports the idea that those dinos we want to see are just back there, 65 million exits behind us. A time traveler just needs to come unstuck in this flow of time, take a shortcut back to the past and viola instant Cretaceous vacation. Watch out for meteors. But wait, things aren't so cut and dried. The truth is that general relativity is formulated according to Einstein's philosophy. It proposes that space and time have a geometry, and physicists and mathematicians usually present it this way, the way he did. If something has a geometry, it must have every point existing somewhere or somewhere. And there is no evidence for this part of the theory because all tests of the theory have been carried out over a very small patch of the universe on the Earth and its immediate environs. Even observations of deep space have been made by looking at old light that has been traveling for millions or billions of years to reach us. There is a problem with the Einstein formula. The problem is that Einstein takes a leap from space-time having a geometry to anything in free fall, that is something not experiencing an external force, following a geodesic in that space-time. A geodesic is a shortest line path in a curved geometry. On the Earth, a geodesic is a great circle path between 2 points, hence it always divides the Earth into 2 equal halves. We all know that if you were to go out on the ocean and follow a constant heading, instead you would follow a rhumb line path, which is not a shortest line path at all. In order to follow a great circle path, you need to make periodic course corrections. In Einstein's curved space-time, there is a mechanism for making these course corrections. It is gravity. But now it seems we have 2 separate pieces to the theory, a curved space-time like the Earth, and a force that makes us obey that curvature, gravity, like the boat captain. Occam's razor tells us that we shouldn't invent things that serve no purpose. So it seems reasonable that if we want to explain gravity, we could just get rid of the curved space-time and keep the gravity. But then we are left with everything happening all at the same time in the same place. We need a coordinate system to keep things separated, but we don't need Einstein's ideas about geometry as much. In 1950, Uchiyama created a version of general relativity that matched this perspective, more or less, called gauge theoretic gravity. Gauge theory then took off and explained all the other forces, weak, strong, and electromagnetic, becoming what is now known as the standard model of quantum physics. All gauge theories have a geometric interpretation, but for other forces it is not seen as fundamental. Still, most presentations of gravity use the geometric approach, which is what it is, and not as a geometry that needs gravity to order phenomena according to geodesics. Let's go back to our highway analogy now. In our Einsteinian curved manifold theory, we travel on a highway and the past is back there and the future is up ahead. In a gauge theoretic version, however, we could be on a treadmill with screens around us showing scenery like some sort of racing simulator. The forces exerted on us are the same in both cases. They are mathematically equivalent. A space-time coordinate, rather than representing a point on a manifold, is an artificial construct that helps us label events as distinct from one another. When I travel from one place to another, the gauge theory tells me what will happen as I traverse that distance. It also tells me how different people, observers in the gauge theory, tells me what will happen as I traverse that distance. Relativity parlance will have different experiences depending on how they interact with the gauge force of gravity. Suppose that the universe is not a manifold. Suppose you are in reality experiencing neither motion in space nor in time according to Einstein's ideas, but interacting with a gauge force that makes it appear as if you are moving. This means that not only is the past not back there somewhere, but other places are not exactly over there either. Rather, to move from place to place or time to time, you interact with the gauge force of gravity, which translates, rotates, twists, and accelerates you like the treadmill. As in the movie The Matrix, other people experience their own versions of reality, which they reconcile by communicating with one another and sharing observations through forces. The universe does not need to be a computer simulation for it to be like the Matrix. That would just invoke another universe that is real, like the manifold we just got rid of, and send Willem of Ockham into a tizzy. As there is no spoon in the Matrix, there is no turtle. While gauge theory has few implications for physical measurements right now, since it is mathematically equivalent to the geometric form of general relativity, it has philosophical implications. If the past and the future do not exist out there, then they could be created out of the interaction between ourselves and the universe, especially when we bring quantum uncertainty into the mix. Our choices could, in fact, profoundly impact what we experience because the future has not been written, and the past has been erased. I say could because we just don't know. I say could because we just don't know. If the history of philosophy is any guide, people will choose sides depending on what they want to be true. I, for one, like the idea that my choices matter and that the future is mine to choose. Those like Einstein will wish for a universe where they bear no responsibility for their actions. If the history of physics is any guide, just when we think we've made sense out of the universe, it will reveal that we still haven't a clue. Thank you so much for watching. See you again in the next video. Until then, as always, keep looking up, stay curious, and dream big.